was going to ask about relationship within some creation applications.
Yeah, exactly. Yeah, so hi, everyone. I would say that probably in contrast to the two talks we heard this morning, which were fantastic, this talk is going to be much more maybe from the practice side of kind of the theory and practice when we think about distribution shift and domain adaptation. So I'm a professor at MIT, but my work is pretty fundamentally interdisciplinary. I've always been very motivated by these sort of very large scale sort of combined social and environmental challenges that we're facing. And so I think a lot about how do we build machine learning systems that help us scale up our understanding of life on Earth. And so today I'm going to be talking a bit about ecological data, and maybe motivating ecological data is a very interesting test bed for these types of distribution shift challenges, but also talking about the complexity of this when we move to sort of these very messy, very large scale real world applications in some of these practical application domains. So my group at MIT works with a lot of different types of data modalities. And a lot of the work that we do is motivated by this increased and sort of exponentially growing scales of ecological data that people are collecting of life on Earth. So we work with everything from satellite imagery to drone data, trajectory data coming from on animal sensors, things like GPS collars or tags, stationary networks of sensors, so things like large-scale grids of camera traps, passive bioacoustic monitoring sensors, sonar, and then increasingly what's called citizen science or community science data, so basically data collected by people to try to contribute to things like the Global Biodiversity Information Facility. So these are things like, how many of you have ever heard of iNaturalist? Anybody go outside? Ah, great, okay. So we work a lot with iNaturalist, for example. So this is very, very large scale human-generated ecological data. And one of the things that basically means that I have never been able to get away from the challenge of distribution shift in my work is that ecological data is just one, fundamentally not collected uniformly, and two, the world is diverse and is constantly changing. So this is just like a very static view of how sort of complex these kind of distribution differences between what we care about and what we have are. So on this side here, we can see this is an estimate of what's called alpha diversity globally. So the number of unique species that exist in any given place on Earth. And on the right, we have basically a heat map of all available species occurrence data. It's about 30 billion records currently that are sort of digitized and standardized. And these are almost anti-correlated, right? So we have a lot more data in places where we don't have as much biodiversity. Access to data tends to be more correlated with things like socioeconomics or something like GDP. And so if you kind of look at what this actually looks like practically, if we want to build systems that work reasonably well, we need to be able to handle a lot of diversity and sort of uniqueness in the deployments where we actually want to leverage machine learning. So this is just one example of the sort of pretty stark differences, both in terms of the bathymetry and the density of fish in river sonar when we're trying to figure out salmon escapement, for example, to maintain sustainable fisheries. You can also see, even within sort of networks of very similar types of data, so these are all static networks of camera traps placed throughout the African continent, that you have both drastic differences in kind of the backgrounds and the species and the subpopulation frequencies across those sites. Or you can see things like if you look at trees from satellites and from the ground, you can see there's significant distribution difference as you go between different cities, just in terms of urban forests. And these are just like a couple of many, many different applications we work on. But one of the kind of consistent threads is that no matter what you do, there are significant distribution shifts in the real world. And I think another important point here is that not only are these sort of different distributions, they're also consistently very imbalanced and long-tailed distributions. The world is made up mostly of a few common things. And then there's this incredible long tail of other stuff. And often that other stuff is really scientifically important. Rare and endangered species are of more scientific importance when you're trying to discover sort of things like their range shifts under climate change than maybe very common species, things like, for example, an American robin, right? So this is just looking at sort of a distribution over species occurrence records in iNaturalist. So we have around 6 million records of American robins, but that as you kind of move down this long tail, you very rapidly see this drop off. So this is a moth from the Amazon, only about 292 records. And then this is a Himalayan wildflower, 16 records. And you can see that there's, a significant extension here. And then, of course, there are many species on Earth. There's estimated to be about 10 million species. So there are many, many, many species where we just have no data at all. So ecological data basically has very complex distributions. And the way that myself and my group and sort of actually many others who work in these spaces kind of think about them is, well, one, there's kind of the simplest version of the scenario, which is you need to be able to robustly identify rare, visually similar, and sometimes even novel categories. And this is maybe like one modality and one distribution, right? So maybe you're just looking at camera trap data, or you're just looking at bioacoustics. You need to be able to do a good job of recognizing things that are rare and that can be very similar to things that are common. That's already a mess. But then if you kind of scale that up, now you actually have these deployments or these distributions from different places. And so you need to be able to adapt to new deployments and identify valuable data for specialized tasks. And this is kind of one modality, but many distributions. And then of course you can extend that even further to kind of the real scenario we work on, where you need to be able to share information and reason across these many different modalities to try to do things like fill data gaps, maybe support scientific discovery, look at things like causality so we can inform decision-making. But now we have many modalities and many distributions of data. And so, as you can imagine, as we move from the simpler scenarios to these more and more complex scenarios, often we start to see a lot of things that in theory should work, don't. Things start to fail. The complexity of the systems is just pretty insurmountable. So in an ideal world, we have this idea that we could build models that are optimal everywhere on everything. And maybe this is like the first talk we heard today, right? This idea that we can maybe build some model that is somehow optimal for every given potential distribution and end user, and somehow changes to the underlying distribution wouldn't change performance. Like you'd just be really robust. But we do not live in an ideal world. And in our experience, this really is not the case. And so, I think many of you are probably familiar with things like the wild data set. It turns out models often don't generalize well out of distribution. And I think the distances or sort of the differences in the extremity of those distribution shifts tends to lead to further out of distribution failures. So the iWildCam dataset, which is the one in here that focuses on camera traps, exhibits some of the sort of most stark distribution shifts of any of these datasets, and is consistently one of the datasets that's most popular in this benchmark because it really captures the extremity of the challenge. And in the era of foundation models, people often will sort of say, like, well, it's fine. Like, we don't really need to generalize or adapt anymore. We can just assume that we build sort of these general models that have these emergent properties, right? There's no such thing as distribution shift when you just have data that captures the entire distribution. But I think there's some recent work, this came out like last week, that I think captures kind of this sort of appearance of robustness versus actual robustness challenge. So here what they were doing is they basically just say, if you sort of are in the ImageNet era, we have ImageNet data, which is in the natural domain. We're taking a really simple version of a domain generalization here, and we're just talking about natural images, so things like sketches or renditions. So in the ImageNet era, things were not robust, right? You just did not see good generalization. In the web scale era, we get a lot of work that says that things are robust. But in fact, actually, we just have rendition data in our training data, right? And what they've done is they've done a really nice filter over all of Lion to remove data that is of renditions. And then they're just demonstrating pretty experimentally that if you don't have in distribution training data, you don't generalize, right? So it's not that the scale is sort of magnificently removing this out of distribution generalization problem. It's just that we're just including distribution data in the training data. And so models turn out to actually still not be robust, even with internet scale data, when you have things that are out of distribution. And I would argue that this is really much, it's emphasizing sort of how much, one, we are not actually seeing robustness or sort of this ability to generalize. And two, if you care about things that are not well captured by things like Lion, like by this kind of internet data, you really still don't actually see the benefits that a lot of people are extolling. And then this is actually I grokked this from Irene Chen, who gave a talk on this yesterday, but it turns out not all available training data is relevant or useful for a given deployment. And so essentially, as training data gets further and further from the deployment distribution, we find it has significantly diminishing returns in terms of its improvement that it gives us. And actually, in some cases, it can be actively harmful. And then even if you're talking about building general models on general data, often we still find that general models are suboptimal for specific deployments. So this is a really amazing work where they built a tree canopy height model for the entire Earth based on JEDI as a sort of a new orbital sensor. And here you can see, like, yeah, in aggregate, this is significantly more accurate than any previous work. But when you actually talk to end users who need to use things like tree canopy height to get estimates of carbon sequestration, what they find is that these global models are never accurate enough to actually inform local scale decisions. So you actually end up needing to build specialized local models to be able to make accurate decisions. And then the challenge is that the relative gain from those global models in terms of your ability to do good local decision making ends up being significantly diminishing returns. So what we find experimentally is, like, if you look at a model trained from scratch over some amount of deployment specific data for fine tuning versus a model that's fine tuned, when you start out at the beginning, there's a significant gap. But as you get closer and closer to good performance, sometimes the trained from scratch model is actually better. And often there's really very little difference between the two. And when you base this on top of the idea that to make an informed policy decision, you need reasonably accurate data, what you end up with is, like, all of the resources we've invested in these global models don't actually give us return on investment versus just collecting local data and training local models. Yeah.
More interested in density estimation? I don't know, for example, for different species. Are you more interested in classification? What exactly is the most pressing question you want to address?
I think it depends a little bit. So the question was, like, what's the question that I'm most interested in terms of understanding biodiversity? Depends a little bit on which data type we're looking at and which users we're working with. We often work really directly with sort of stakeholders or users. I'm very interested in rare species categorization. This is something that models really struggle with. I'm interested in individual identification to do non-invasive mark recapture-based population estimation. And then we also look at density-based population estimation from different modalities of data. So that's trying to get at, like, how many of a given species there are in a given place and time. Then we also look at sort of more traditional ecological metrics like distribution or occurrence of species. So trying to map the spatial extent of given species and understand how that's changing. Yeah, and then, sort of as complementary to that, sort of broader scale ecosystem level metrics, like how do we think about things like functional diversity from large scale data?
I asked also because you, sorry to ask you.
No, it's okay.
You talked about decision making a few times. Which decisions are those about, actually?
Yeah. So, I mean, there's a bunch of different types of stakeholders and different types of decision makers in this space, right? So we work with everything from really local scale decision makers, which is things like protected area managers who are making decisions about how to allocate resources to try to protect species, or things like the Alaska Department of Fish and Game. They're making every 4 hours policy decisions around fishing quotas. So you need to be able to understand fishing escapement. But then we also do stuff like work with more global scale policymakers. And then there it's things like, how do you do spatial prioritization over what land we should protect? So there's a lot of different types of decision makers that need different things. And I think global scale models are useful for global scale decisions, but local scale models are necessary for local scale decisions. So there's a bit of a dichotomy.
So, quick question.
Yeah.
This picture that we see here, is that just a generic observation, or is there a more exact experiment that shows something like this?
Yeah, this is a generic observation that comes from many, many exact experiments over many different types of data. So this is the work of mine and many others as well. Working with things like pre-training versus specialized fine-tuning for things like iNaturalist or these camera trap data sets, but then also working with things like satellite imagery, trying to do something like crop type mapping. So these trends, I would say, are, I made a really generic figure because it's sort of, I found it to be true over many different types of experiments and types of modalities of data. Yeah. Cool. So local decision makers need specialized models, essentially, to be able to make informed decisions. And so one thing that you can think about doing, and I'll take a bit of a detour here, is think about adaptation, right? So mechanisms for taking a general model and then adapting it to a specific distribution. And so here, maybe this is adapting it to a river on the Kenai, or sort of a specific location on the Elwha, or we're just recently started working with the Klamath Dam removal. And so here you're looking at a bunch of different locations up a previously unstudied area. So you need to be able to generalize and adapt to new distributions. And this is a really, like this particular problem where you're trying to just count. So you're basically tracking to count escapement of salmon. It's very simple because you don't have categorization. It's just counting fish. So it's a class agnostic problem. And we've found that class agnostic problems tend to generalize a lot better than class specific problems, particularly when you have this type of subpopulation shift. So being more generic gives us more robustness. So I would just like to emphasize that like the results I'm showing are like probably optimistic relative to trying to do similar things when you have these imbalanced changing subpopulations. But okay, so unsupervised domain adaptation is something that's been studied for a very long time. This is like kind of a high level view. If you took sort of all modern advancements in unsupervised domain adaptation and you kind of put them all together, what we found is, while unsupervised domain adaptation looks good in theory, and often on fixed data sets, we're not seeing it get used very often. And if you're not seeing something get used very often, the kind of the question is like, well, it must not be working. Why isn't it working? And so here, the idea is you have labeled source data. In this case, we have labeled source data from quite a few different rivers, but we've also tried this on a bunch of standard data sets, things like cityscapes to foggy cityscapes, which we can talk about like fake benchmarks all we want. It's basically like a data set of fake city data where then you've added fake fog to it. So it's like, it's not necessarily super representative of real distribution shift, but it's a really common benchmark, so we still have to consider it. And then the idea is you have unlabeled target data. And so then somehow within this framework, you're going to make some effective, effectively adapt the statistics of the model to this new target, but you don't want to forget too much about the source or the underlying distribution. So what we did is we basically explicitly identified or noticed that most of the recent work in the space was somewhat duplicative. A lot of it was just different combinations of the same components with slight variations. So we just built one unified framework to try to actually really be able to systematically compare recent methods. And we published some really nice, easy to use code. So if you guys are doing distribution or domain adaptation specifically for object detection, we have, I think, some nice starting points. And just to kind of point out that like all this, recent work is actually just some combination of these components. These are basically like the 5 sort of most common state-of-the-art methods from the last, 5-6 years. So one thing that we found almost immediately is that we're all lying to ourselves about progress, unfortunately. So it turns out that when people are thinking about measuring the value of domain adaptation, the trend in benchmarking is comparing to a source-only model that's basically the simplest model you can think of. So you have your source, you have data that's just trained on a source, and then you're supervising it through comparison, and then you just run that on your target data, but with like no bells and whistles. And then you're comparing that to this type of complex domain adaptation method where you have a lot of kind of fancy training techniques that have nothing to do with the target data being available at all. So one thing that we would really argue is that the real goal should be comparing with a lower bound that is just all the fancy components you have in your method that aren't related to the target data. So essentially, we found it's really important to include reasonable sort of source augmentation and EMA when you're actually doing these baselines comparison. And then, so, you should have some fair informative source only model when we're doing these fair comparisons. And then similarly, if you want an upper bound with supervised target data, you should also make sure that your Oracle model is somehow fair and informative. And so what we found is that people weren't doing this. And so what we had was, here's like prior work, reported baselines, reported oracles, and we're seeing progress that starts to be better than an oracle. And anytime something sounds too good to be true, I think it is, right? Like, it doesn't make sense that a domain adaptation model would be better than a model that has labeled distribution data in distribution, right? The fact that most of these methods were claiming that their method was somehow learning more from unlabeled data than we had with human labeled data was fishy. And what we found is that when we sort of re-implemented this in a nice, systematically, fairly compared way, where we sort of didn't have all these extra bells and whistles being given to the method, that the oracles and the baselines significantly went up, and the baselines were now better than most of these methods as reported, right? But then if we actually, we want to be fair to the methods as well. So we regenerated the baseline results, and we found that some of them really were doing better than sort of having no access to target data at all. But there'd been essentially no improvement over the last 5 or 6 years. Nothing was really much better than unsupervised mean teacher. Yeah. Yeah. So essentially, they were all comparing to like very, very simple baselines. And then they were saying, okay, our method has this really nice way of leveraging unlabeled data, but they were giving their method a bunch of extra bells and whistles, things like exponential moving averages and sort of like really strong augmentation in the source data that you should actually include in a comparison to a baseline, I would say, because it doesn't have anything to do with adaptation. Yeah. And we found that those things that were sort of not being reported were having really outsized impact on performance.
That's all vision.
Yeah. Cool. So we haven't seen a lot of progress, actually. But now we have this nice systematic framework where we can do really nice fair comparisons. Yeah.
Is there a way to kind of know that now you raised the bar, but maybe like somebody else can say, oh, what you're doing is also just a lower bound, and actually you're also not, you could also do it better, and the bars are actually higher. Is there some way that we can really say that there's something that I'm really getting, that I am or I'm not getting by the augmented data without the, that I cannot replicate by just improving the model?
Right. So I think we are seeing that there's benefits over a baseline, and I think the point here is that you're doing the comparisons fairly.
The benefit over your baseline. I don't
Sure.
know somebody else. I mean, the same way. That
No. So
somebody else could base the baseline.
yeah, but then arguably, as long as you're doing these comparisons fairly, so you're basically giving the different models you're training access to the same components. I think you can't guarantee, of course, because things might be different, and of course, there's an essence of like how much hyperparameter tuning you can reasonably do for any of these things. So of course you can't guarantee, but I would say that you can do a lot better than just using completely different underlying code bases and not giving access to the same sort of components of a model. But no, I can't guarantee that the baseline wouldn't necessarily go up. I think my point is if there's a way to make the baseline go up, and I'll talk about that a little bit better, like you can just use a more modern architecture, for example, all of those things go up, right? So as long as you're continuing to try with our best effort to do fair comparisons, I think at least we're still better than not trying. But it's really hard to compare against models, I would say. Mm-hmm.
So then you took the one with the most bells and whistles at the baseline, because for each of those, probably there is a different, they use different kinds of bells for the source.
Yeah. So we essentially said, that we took like the best one that didn't have any access to target data as the baseline, but that had access to the same sets of bells and whistles. So they had access to these pieces, right? So, and like just talking through this a bit, like,
What does EMA stand for?
exponential moving average,
Okay.
which is one of these like, EMA makes such a big difference and no one really understands it. I would say. Like it makes such a big difference across the board. I think, like, for example, when they were trying to train Dino, they really tried to not use EMA because they were like, this thing is really weird. And they couldn't get the results to be nearly as good without it. Just this like, basically like way that you sort of let the weights update with some exponential moving average ends up being really important for high performance. Yeah. Now I'm like, I've tried now to think about like, well, how do we better understand EMA? And I haven't quite come up with an experimental setting like what you were talking about, where I really believe that I would sort of understand how we are just changing this one dimension. So, cool. So now you have all these different components, and you can actually do some sort of nice systematic experimental analysis at least. And what we found is that one, which is like a positive, I think, from the benefit of robustness side, your network initialization has a really outsized impact, and starting from a better model tends to be much better. So here we're looking at an oracle model, and if you add, for example, strong augmentation and exponential moving averages, that model significantly increases. But then also just from your baseline model, if you just add strong augmentation, you get much better. If you just add EMA, you get much better, and the combination is significantly better. So this network initialization is a pretty important dimension. And I would argue that like better starting points tend to be better adapters. And then again, like these sort of previously unreported hyperparameter settings, so a lot of things that just weren't reported in these papers where we had to like dig really deep into the code to figure out what settings they were using, had really significant impacts. So just things like batch composition, like the ratio between source and target data in the batch, was changing performance by about 15%. And then there's been a lot of effort and put into looking at this sort of need to do feature alignment. But we found that feature alignment versus the computational complexity really had significantly diminishing returns. So if you just looked at feature alignment alone, you got some pretty nice boost, 2.6%. If you just look at a distillation-based loss, you got about a 4.6% improvement. The combination of the two, there was like very little sort of complementary benefit. Putting it all together, okay, cool. Like we can make a method that has slightly better results, but really this is more of an experimental study. And for me, it was more trying to understand, why aren't people using these things? But the nice benefit of this is now we have this really nice systematic code base where we're able to get these things to work well enough to use. So we are using them on our fish data. And relative to your question, if you swap this out from like a ResNet backbone to a VIT, just all three of those go up, right? So yes, the needle can change. But if you have something like a nice way where you can easily compare things, at least it's easy to understand how that needle changing changes the result of your method as well. And I do think it's interesting that the relative gain from some of this adaptation stuff seems to diminish when we move to a VIT backbone. So it's like, maybe there's more room to improve. A lot of these things were designed on top of VGGs, so who knows? Okay, so yeah. Yeah. This is just illustrative. In the paper, we have nice error bars.
So these differences are meaningful?
Their differences are meaningful. Yeah. Okay, so that's one mechanism to specialize. There's a lot of other kind of interesting, I think, mechanisms to try to specialize these models that we do actually use in practice. So this is kind of obvious, but you can try to learn a prior that helps you basically remap your probability distribution based on where and when you are on Earth. This is really nice. You get sometimes like a 10% improvement in species classification. A lot of that has to do with the fact that you have multiple species that'll look really similar, but they don't live in the same place. So it's not actually a problem you need to solve. But the challenge we have with this is that we're learning these priors on historical data, and species ranges are shifting. So now what we have is priors that are absolutely almost suppressing our ability to recognize when things are changing. So we use these in practice, but there's a lot of kind of human verification mechanisms that get built in when we do something like this for a naturalist or something like Wildlife Insights. We're also quite interested in how you take foundation models and make them runnable by an organization that doesn't have large-scale GPUs. And so this was some work with Dan Alistair But we showed that you can actually really efficiently specialize while compressing a model, and then you get much, much more efficient models because you let them specialize. And there's like some kind of cute things you learn. Like if you try to specialize a generalist model to sharks, it like basically learns to forget the red channel, which is cool. But one of the things I've been increasingly interested in this kind of era of like large scale public data sets that are somewhat more general is this question of whether we can actually instead do dataset subset selection as a mechanism for specialization, potentially also without requiring labeled data from a given deployment. So the idea here is like often when we're talking about these like potentially like multi-deployment or multitask settings, we have some sort of large scale subset of data. Maybe you use something like a data filtering network and you find that, okay, actually this is the subset of data that's most useful across all of these tasks. And you're doing some evaluation in aggregate. But what we are quite interested in is kind of how do we come up with good methods for selecting subsets of training data that are most relevant to a given deployment, right? So you have some general model. I want to know how to best fine tune that model for a specific user to get the best possible starting point given that their distribution. And the assumption here is that you could either have no labeled data, but unlabeled data, or you could have some amount of kind of like labeled validation data for a given domain. We've just started kind of digging into this a bit more, exploring this kind of deployment specific data value. I think there's other reasons that it's important to understand data relevance that are much more about things like understanding the value of pushing for data sharing. And as data kind of ownership and sovereignty and risk and the resources that it requires to kind of share data publicly become more and more of a concern. I just came from the COP about a week ago, which is like a large-scale biodiversity policy forum run by the UN. One of the biggest ongoing conversations is about data ownership and data sovereignty. And so now if we want to build generalist machine learning models, we'd better be really transparent about what data is going to have what value for who when it comes to training these general models. Because otherwise we're telling people, yeah, give us all your data and we will build a model that is optimal for you. And in practice, that's not always the case. And often these general models are suboptimal. And what we see is that local scale data sharing, which might be a sort of a different mechanism for thinking about data ownership, can have really almost the same or sometimes better performance for local scale users than something like a general model that's global. So we've been really exploring this experimentally for different application domains, things like iWildCam, AutoArborist, but also stuff like Geode, which is Olga Rusakovsky's recent work at trying to build a geospatially diverse test set for ImageNet. And it's work in progress, but some of the things we found is we can find more useful data subsets using knowledge for basically almost everything. And particularly as the distribution distance, the sort of the distance in the distribution from the aggregate training data to a specific deployment is larger, then the sort of relative value of this subset selection goes up. And also a lot of current methods, things like core sets, data filtering, seem to focus on quality over relevance, right? So we don't necessarily have methods that are good at understanding relevance. They're just good at understanding quality. Yeah. Mm-hmm.
So is the idea that instead of fine-tuning with the target data from the generalized model, you should first fine-tune just with the subset data first and then introduce the target data, or include the target data with the subset for fine-tuning?
So I think both scenarios are reasonable for different sort of potential applications, but we're considering both. So both the sense where maybe you have shared some of your data in a public sense, and so now you could just subselect your data, and that's maybe a comparison. But particularly because these distributions are very long-tailed, I mean, just a naive thing is like sometimes sampling from other more diverse distributions of things that are rare can be really beneficial for performance, because from your data alone, like rare species might not be represented enough. So like really dumb heuristics are just like sample from other data so that you can try to get sort of fill up in the long tail. But you could also imagine the scenario where you haven't actually put any of your data in some public resource, and now you just want to get the best possible starting point to do something like active learning or domain adaptation. from a general pool. Anyway, access to labeled deployment data tends to still be the most valuable thing. So if you do have access to labeled deployment data, sometimes it's really hard to beat that, right? These things can be highly specialized, and highly specialized is hard to beat with less relevant public data. Cool. So just a bit philosophical, but zooming out, thinking about this trade-off between sort of global generalizable models versus specific models. One question I think is quite important, it's relevant to what you brought up earlier. Who is the user, right? Like, who is the person that needs this model and what do they need it for? And I think we need to do a better job of kind of thinking about not just data point scale evaluation, but really evaluation in the context of the downstream decision. You know, what types of mistakes are actually reasonably important given a decision you're making. If you make a lot of mistakes on like mule deer, maybe it's not going to actually change anything about your policy decision versus making mistakes on something like wolves. Another interesting dimension is kind of like not just, you know, what data do they have, but more broadly, what resources does that user have to enable their own specialization of a model? So one thing that's definitely true is it's not super sustainable to need to build a custom model for every single end user, right? Like it's not something we could do very well. And so if the end users themselves can specialize models, that's good. Often that's also not the case. And then so maybe the best, more sustainable starting point is something like you make your best global model, and at least it's kind of better in aggregate. Then you have to be really careful about the decisions you're making about which global model is the best global model. And we definitely have the case like what Irene was talking about with things like iNaturalist or Wildlife Insights, where if you add new data from a different country, it might actually specifically harm performance for another country, like in a biased way. But so do they have access to data? Do they have access to data that has labels? Do they have their own compute? Do they have the expertise to train a model? And do they have bandwidth to move that data from where they've collected it to the cloud? And all of those things are factors that pretty much define the space, the action space you can work in. And then how unique are their needs, right? So if you're a new national park and there's been a really like well-resourced national park that's right next to you, that's already trained a really good model for them, and all of that data is public, then maybe you don't need too much specialization. But if you're sort of representing much more unique needs, then somehow the cost of getting a model to work well for you can be significantly higher. Cool. So thanks for following me on this journey of like practical challenges in ecological data. None of the work is possible without a huge network of collaborators, not all of whom are even on this slide. But yeah, I'd be happy to take more questions.
We definitely have time for questions. So
Yeah, so it's like, it sounds like the foundation modeling paradigm is like leading to many issues downstream, like given what is at stake with species diversity on Earth and so on, like isn't it worthwhile to consider endeavors that would use foundation models or ecological data, and that would be carefully designed and pull data from various places and so on.
Yeah, we're doing that. But the underlying problem is still there, which is that these foundation models that are, if a model that's best on aggregate is not the same as a model that's optimal for everyone. I mean, that's most of the theory we were talking about this morning is talking about the same problem. And so if you actually need to make decisions, you have some accuracy you need to hit to make decisions. If your foundation model can be above that accuracy and you can reasonably understand the uncertainty, then great. But we don't have representative data in enough places on Earth that that's actually true right now. Even if we pool sort of all of the data we have, or we collaborate with groups like iNaturalist, it's like 200 million species observations in iNaturalist, right? That's large scale, but it's biased. So.
But I mean, like also, like, you know, is the paradigm of like generalizing and specialized like something to reconsider? That's the current paradigm. Like you have a deep foundation of it, which you can specialize.
Yeah. I don't know that it's like needs to be fundamentally different. I guess all I'm saying is like, maybe we need to think up, you know, so for example, this idea of like, once you have more general training data, do we need to rethink how we select data for that specialization? Is like something that I would argue has not necessarily been super well covered in the literature, but I think is more and more relevant as the data becomes more and more comprehensive. And then, you know, yeah, we work on things like domain adaptation because it's a general model, you try to specialize it. But yeah, I guess maybe the point I'm trying to make, which is maybe not that spicy anyway, is just like, you can't just generalize. It's not yet sufficient for me to just generalize. And foundation models alone do not seem to sort of match the needs of the users I work with.
All right, so I guess we have to generalize in a specialized. So we unfortunately don't have much more time for. Would you start setting up, please? So I'll only take one more question from somebody who hasn't asked questions. Please.
So you brought up the challenge of like the long tail distributions. Because like, of course, domain experts always really only care about these. So do you have any like does your ALDI framework kind of go in that direction already, or is it ongoing work, or what's your experience?
Yeah, long tail is super hard. Usually when we actually are dealing with a long tail in practice, we have some mechanism for human input, right? Just like practically, we can't get good enough results in the long tail trust an automated model. So we use fancy versions of selective prediction and something like that. I don't think like, so all the things that I was comparing that on, those don't have a long tail distribution, right? Like I pointed out the fish data, it's just differences in density of fish, but it's not actually different categories. And we have tried this with camera trap data, and just the relative gains across the board are lower. So you do still do a little bit better, but it's often at the expense of the long tail. Like, yeah.
So yeah, ongoing frontier.
Ongoing frontier. And I think when the long tail is fine grained, it's just a total mess. Like it's just really, really hard.
All right, so let's thank Sara again.